In this video, I'll be teaching you guys about transformers and how to solve for the voltages and currents past transformers inside of any circuit. First thing I want to say is that transformers turn voltage into current or current into voltage. Okay, not really necessarily what I said there, but basically, if the voltage goes up with the transformer, the current will go down. And if the current goes up, then the voltage will go down. And this is actually very useful when it comes to like long distance circuitry, right? Especially the electrical grid. Because transformers can increase the current, which thereby decreases resistance along copper lines, right? Or along whatever metal wire that the electricity is traveling by. And then when, like, maybe you've seen those poles, right? You've seen the poles with like a little box, like a circular box outside of your house? Those are called, well, my professor told me, those are called pigs on poles, like a pig on a pole. And those are transformers. Basically, the electrical grid increases the current super high, but what those pigs on poles do is bring it back down and bring the voltage back up to a point where you can use your electronics for. Now here's the thing about transformers, they can only be used with alternating current. You can do the same with direct current, right? You can still transform it, but you wouldn't use a transformer. You would have to take some other steps. But transformers look like this. Basically, you have two little curly lines parallel to each other. You might sometimes see two straight vertical lines in between them. This just stands for an iron core. An iron core would kind of just look like this, a circular, like a circular thing, where you would have some wire and you would wrap coil. Oh my god! You wrap. Bro, the kimchi is making me choke. You wrap like coils around the wire like this, kind of. At the end there'd be like another coil, right? Maybe there's only one wire this time or something like that. No idea. Right, something that looks like this. And the reason why I'm stating this is because the amount of coils, right, the amount of times that you spin this wire around this iron core is what determines your transformation, I guess you could say, factor. Okay, so the amount of coils on the entry side of your voltage or current is your N of P, primary. P stands for primary, and the amount of coils on the the output side of your core is called N of S, which is secondary. And you have voltages at your transformers. So the voltage of your transformer before transforming is called V of P, and the voltage after transforming is V of S. And the current before transforming is I of P, and the current after transforming is I of S. And let's go ahead and cover all the formulas related to this. So in order to calculate secondary voltage, you simply need to multiply your primary voltage by N of S over N of P, and this is equal to V of S. All right, this is just how you calculate V of S, or your secondary voltage. And you might be wondering, how do you find V of P? Well, KVL and KCL all still apply, right? This has a positive and negative end, and this has a positive and negative end. You can just use KVL, counterclockwise, clockwise, doesn't matter, to determine the voltage at this transformer, the primary voltage at the transformer. The thing about current is that it's the exact opposite. Okay, so the current is N of P over N of S is equal to I of S. All right, so basically the primary, to get the secondary, you basically just flip over your amount of coils on the secondary and primary side into you just flip them over as fractions. All right, so this is N of S at the numerator. Now it's primary at the N of P in the numerator for current. So these two formulas are basically how you calculate everything for transformers. Everything else you use for transformers, all the same laws. KVL, KCL, Ohm's law. Everything is still the same. Let's go ahead and work on some problems to show you how to do this. Now, for this problem, you have 5 coils on one side or 1 coil on one side. More specifically, that's the ratio of coils on the primary side and the secondary side. Right? This could have been like 5,000 to 1. Right, but if you could simplify the ratio, why wouldn't you? Correct? Right? It's way easier to do math with 5 and 1 rather than 5,000 and 1,000. So it simply represents the ratio, and again, the math will always be the same, no matter what ratio you have, as long as you do the simplification of the ratio, right? But let's go ahead and do this. Well, we can do KVL along this loop, and if you do KVL, you're going to figure out that you have a voltage rise in the counterclockwise direction for VP and a voltage drop for this voltage source here. Therefore, VP is equal to 5 cosine of t volts. Maybe I should have put volts here. Let's put volts here. All right, now that we find the voltage of the primary voltage of this transformer, we can use this formula to find the voltage of the secondary transformer. So let's go ahead and use the formula. V of P is times N of S over N of P is equal to V of S. So if we plug in all the numbers that we know, we have 5 cosine of T. 5 cosine of T volts times N of S over N of P. N of S is 1, right? And N of P is 5. So once we have this, it's just 5 cosine of T volts times 1/5. And this just goes into 1 cosine of T. 1 cosine of T volts. So V of S is equal to simply just cosine, let's use a good color, orange. Orange is a good color. Cosine of T volts. All right, now that we have that, simply, again, we can use KVL. So this right here, V of L, I wrote L as a subscript rather than R because maybe at the end it would just be a light, right? You'd just be powering a light. So L just stands for light, okay? This could be a light bulb. Light bulbs are resistors as well. So if I use KVL here, we're going to figure out that. So if I put KVL here, these two are KVL. We'll figure out that V of L is actually equal to V of S. And V of S we calculated was cosine of T volts. Therefore, V of L is equal to cosine of T volts. Okay, well, once we have that, we can use Ohm's law to find the current I of L. Right? So to solve for the current I of L, let's use Ohm's law up here. You just use V of L divided by 5 ohms. So cosine of T volts over 5 ohms is equal to I of L. I of L simply equal to 1 over 5 cosine of T amps. I of L. Let's go ahead and circle this because this is important. Keep this in mind. Okay, let's not overlap the equations. All right, well, once you find I of L, you're going to realize that these two are in series, correct? I of S and I of L are traveling the same path. Therefore, I of S, if I use a little bit of KCL, I of S is equal to I of L, which is 1/5 cosine of T amps. All right, if we use the transformer formula, transformer for current, we can actually isolate I of S. Well, how do you isolate I of S? You can just simply use the formula. I of S times N of S over N of P is equal to I of P. Right? All we did is do a little bit of algebra to move this guy onto this side of the equation. Well, once you have this, you can rewrite your equation. So you get I of S, so I of S is 1/5 cosine of T amps times N of S over N of P. N of S is 1, N of P is 5. So we have, oh, that's really bad handwriting. Let me fix that. Let me fix that for you guys. A times 1/5. This is just simply equal to 1 over 25. Okay, running out of space. 1 over 25 cosine of T amps. And this is equal to I of P. Well, once you solve for I of P, you solve for everything, right? So we have V of L, the voltage at the light. This is a check mark. It's good. We have V of P. We have I of P. We just solve for it here. We have I of S, right, KCL. And we also have I of L, 1 over 5 cosine of T amps. We also have V of S. Don't forget about that. So we just solve for the circuit. So let's go ahead and solve this circuit. Basically, we have a ratio of 20 to 4 coils. Now, here's the thing about this. We can actually simplify this ratio. All right, 20 to 4, well, can be simplified to 5 to 1. So this ratio, if you don't know how to simplify ratios, you might have to go back to elementary school, buddy. But now we can do math easier. Who wants to do math at 4 and 20? We can use 1 and 5. Right. Smaller numbers make the math easier. So let's go ahead and start off this problem with KVL. Most of the time, you're going to start off with KVL, trying to find the voltage, your primary voltage. Sometimes the problem does give you the voltage at the light first, right? So you can do that as well. But let's go ahead and use KVL. So if I use KVL here, we're going to figure out that V of P is equal to 100 sine of T volts, right? So V of P is equal to 100 sine of T. If we use the transformer formulas, they're going to get V of P times N of S over N of P is equal to V of S, correct? Let's go ahead and plug everything in that we know. So 10, so we have 100 sine of t volts times n of S over n of P. N of S is 1, n of P is 5. So 100 times 1/5, right? It's just simply 20 sine of t volts. And this is equal to V of S. All right, once we solve for this, again, we can use KVL. So this right here was KVL. So we're going to write another KVL equation. V of S is equal to V of L, which means that and we solve for V of S here, which means that V of L is equal to 20 sine of t volts. All right. So since V of L is 20 sine of t volts, we can use Ohm's law to solve for the current, I of L. So voltage divided by resistance, this time it's 10 kilo ohms, right? 10,000 ohms. We can solve for the current. All right, so we could turn this to 10,000, right? 10,000 ohms, and divide 20 by 10,000. 20 divided by 10,000 is 2 over 1,000 sine of t amps. Okay, and this right here was I of L. Now the thing about this is that who wants to look at this sloppy junk of mess when you can just write down 2 is equal to 2 sine of t milliamps. Right? So milliamps just stands for 1,000th, so 1 over 1,000 amps. Right? And in this case you have 2 over 1,000 amps, which means that you have 2 milliamps. So I of L is 2 sine of t milliamps. All right, let's go ahead and solve for I of S. Well, I of S is just simply equal to, this is KCL, right? I of S is equal to I of L, 2 sine of t milliamps. All right. All right, now we can solve for I of P. So if we use the transformer formula for I of S to I of P, we get I of S times N of S over N of P is equal to I of P, correct? Let's go ahead and fill out this equation. I of S is 2 sine of t milliamps, and N of S over N of P is 1 over 5. So now that we have this, just multiply this by 1/5, and then you get that your I of P, your primary current, is equal to 2 over 5 sine of t milliamps. And there you go. We solve for everything. Now, I didn't write down I of the current at this voltage source here because it's kind of self-explanatory that your current at the voltage source will be equal to the current of your primary transformer, right? The current at your primary transformer. But also, IFS and IFS are the same variables. Well, we have a more complicated transformer circuit now, but basically first thing I notice is this 10 and 25. This ratio can be simplified into, right, 10 and 25. Ratio 10-25 can be simplified into 2 and 5. All right, so let's move 2 and 5 onto your ratio for this transformer. Let's go ahead and do the problem. First things first, KVL. Most of the problems, if you get your voltage of the voltage source, you're just simply going to use KVL first. KVL to find the voltage of your transformer. So KVL, so your VP of 1, this guy, VP of 1, is equal to your voltage at the voltage source, which is 23t, 20 sine of 3t. Now this 3 represents angular frequency, okay, if you know about alternating current and angular frequency. But the thing is that the 3 really doesn't matter, okay? Whatever value you have inside of your voltage, your sine function or cosine function, whenever you're using transformers, it's not going to change anything since you're not finding any derivatives or doing anything with the phase shift or anything like that. Right? That's going to happen when you work on capacitors and inductors. But let's go ahead and focus on topic, actually. KVL gives you that VP of 1 is equal to 20 sine of 3t volts. Okay, so V of S, we need to solve for that. So VP of 1 times n of s over n of p is equal to Vs of 1, correct? So Vp of 1 was determined to be 20 sine of 3t volts, and n of s and n of p are simply 5 over 2, correct? Times. So this right here turns into 50 sine of 3t. Let's fix that. 50 sine of 3t volts. All right. So this is your V of s of 1. Sorry. All right. Now that we found Vs of 1, again, we can just do KVL around this loop. All right. So KVL gives us that Vs of 1 is equal to Vp of 2. Therefore, Vp of 2 is equal to 50 sine of 3t volts, right? All right, now that we have that, we can use the transformer formula again to solve for Vs of 2. So Vp of 2 times Ns over Np, right, is equal to 50 sine of 3t volts times N of S over N of P, which is 15 over 2. And if you evaluate this, I just plug it into the calculator. You get 375 sine of 3t volts for V. That's actually right. Put in a green box for Vs of 2. All right. Again, KVL. How helpful of a tool, right? KVL. Wow, we used this like 3 times this problem. So KVL. Okay, let's just write another KVL line. KVL up here gives us that Vs of 2 is equal to V of L. And V of L is equal to Vs of 2, which we determined was 375 sine of 3t volts. All right, now that we got this, we can use Ohm's law to divide the voltage at the resistor over the resistance to get current. If I were to just plug this into the calculator, I should get 1/8 technically. So 1/8 of the sine of 3t amps. And I can also represent this as 125 sine 3t milliamps if I wanted to. So this is equal to I of L. All right, this guy. I of S, simply KCL, is equal to I of S of 2 is equal to I of L. I'm not gonna rewrite it. That's kind of annoying. So we can use your transformer formulas to solve for IP of 2. So IP of 2, actually, let's isolate that. IS of 2 is equal to NS over NP. Sorry, what am I writing? Wow. All right, this equal sign gets erased. And this should be equal to IP of 2, correct? All right, if we set the equation, we should get, okay, I'm running out of space. Let's erase this KCL, since that's self-explanatory. Make more space. So this is 125 sine of 3t milliamps times N of S over N of P. N of S is 15. N of P is 2. All right. And what you should get is 125 divided by 2 times 15. What you should get is 937.5 sine of 3t milliamps for your I P of 2. Right, this guy. All right, I of S 1 is equal to IP of 2, right? This is just series circuits or just KCL. All right, once you have this, I think we'll barely have enough space to find IP of 1. So IS of 1 times NS over NP should be equal to, so IS of 1 is just equal to IP of 2, so we can just replace IS of 1 for IP of 2, which is 937.5 sine of 3t times n of s over n of p, which is 5 over 2. And if you do this, okay, this should be, if you do this, you should get 2,343.75 sine 3 of t milliamps for IP of 1. And IP of 1 is just equal to I of S, right? The current at the voltage source. So yeah, this is transformers. Honestly, the only thing that you're learning new is these formulas. But if you understand the math well enough, and even if you understand the concept well enough, like you could pick either one. It's just, the only thing that changes is these formulas, okay? Like everything else is just KVL, KCL, Ohm's law. It's all still the same to solve these circuits. You just gotta understand which one's N of S and which one's N of P, right? N of S is just the ratio of the coils on the right side. N of P is just the ratio of the coils on the left side of your ratio. So, as always, if you have any questions, put it down in the comment section. And if you found this video helpful, consider subscribing and liking the video. Thanks for watching.